Hey, Wheat North, Mr. Yergler here. We need to talk about the common ion effect. This is kind of something that we've already talked about. We've just never really applied this term. So let's take this reaction as an example. There's a cobalt chloride complex that we've used in the past. It turns pink on this side and it's blue on this side. And in the past, we have manipulated this by adding a different reactant, right? We added lead nitrate to it. And when you add lead nitrate, nitrates are always soluble, and so what we really are adding are just lead ions and nitrate ions, right? And we can shift this equilibrium. It's a temperature-dependent equilibrium, so we can shift it by temperature, but you can also shift it by manipulating the concentrations of the ions, right? And when we added the lead nitrate, the lead ions kind of grab onto the chloride ions and form the solid lead chloride, which precipitates out as a white solid, right? And then that, because you're pulling those chloride ions out of solution, we're going to be shifting the equilibrium to the left side, right? Which it made it more pink. You may remember from doing that in class. So we can shift the equilibrium by pulling out an ion. We can also shift the equilibrium by increasing the concentration of an ion, right? And we've talked about situations like that in the past. This is where we get to what's called a common ion. If you add an ion that's part of the reaction, but you're adding it from a second source, it's referred to as a common ion. So in this example, calcium is a common ion between these two compounds, right? So let's take our lead chloride solid that's precipitating out. Now in the past we've said that this is insoluble and so it comes out of solution, but now that we've started talking about solubility equilibrium, we now know that it's not really 100% coming out of solution, it's mostly coming out of solution, but there are some ions present at an equilibrium. Now let's say that you have this equilibrium and you want to reduce the amount of lead ions, which is often the case because lead is a toxic ion. What you can actually do is add really a harmless salt, and that can affect the equilibrium. So let's say we put some sodium chloride in the solution. Sodium salts are always soluble, so that's going to be soluble. And the relevant ion here is the chloride ion because it's common in this equilibrium. So what we're doing is we're actually increasing the concentration of the chloride ion. Which way does that shift the equilibrium? It's going to shift it to the left. And in the past we've talked about this in terms of reactants and products, but now that we're talking about solubility, what's really happening is we're making the lead chloride less soluble, right? Because more of it is going to reform to form the solid and reduce the concentration of the lead ion. This is what's referred to as the common ion effect. The presence of a common ion always shifts the equilibrium so that less of that substance will dissolve. This is kind of another way of saying it. Any salt is less soluble in the presence of a common ion. And this kind of explains pH's effect on solubility, which we'll talk about in the future. But if you affect the pH, if you manipulate the pH, what you're really just doing is affecting the concentrations of H plus or OH minus. This also has incredible applications for things like oceanography and geology and climate science as well, because there's all kinds of complex equilibriums that are at play in things like the ocean or in lakes and streams and stuff. Limestone is calcium carbonate, which is normally insoluble, but we know that everything that's insoluble at least dissolves somewhat. And that's in equilibrium with the calcium ion and the carbonate ion, which is in equilibrium with water with the bicarbonate ion, which is itself in equilibrium with the carbonic acid, which is in equilibrium with carbon dioxide gas, right? So if you manipulate the pH, if you change the H plus concentration, then that affects each equilibrium, because now you're pulling OH, you could be possibly pulling OH out of the solution to form water, which shifts that equilibrium, which reduces that concentration, which shifts that equilibrium, right? You could end up with a lot more carbon dioxide dissolved in your water, which could affect the pH, and that's going to affect all kinds of other things. This is a really cool graph. So this is showing these three equilibriums kind of at play with each other. Carbonic acid is predominant at low pHs, which makes sense because we have so much H's, and so it's going to protonate that CO3. As you increase the pH, you're decreasing the H plus concentration. That affects the equilibrium. You have less carbonic acid and more bicarbonate ion. So at a pH around 8 or 9, it's predominantly bicarbonate ion. Continue to manipulate the H plus concentration, and eventually the CO3 minus 2 is the predominant ion. And this is really all because of the common ion effect. As we manipulate these ions in the solution, that's going to affect the equilibrium of anything that has that ion also in its equilibrium. I found this great video that kind of demonstrates this or shows it. And it has its own narration. I'm just going to go ahead and narrate it myself. So imagine we have silver iodide in solution here. And silver iodide is slightly soluble, so a lot of it is going to exist as a crystal, as a solid, which we see right here, but there's some equilibrium going on between the ions, right? We're still dissolving and reforming the solid crystal. Now let's say we add sodium iodide, which is what this is that just kind of entered the picture. This is quite soluble, so it's going to break up into its ions. And because we're increasing the concentration of the iodide ion, it's going to want to reform. It's going to shift the equilibrium to the solid silver iodide. But the only way it can do that is to grab more cations of silver. So it actually reduces the amount of silver in solution. The iodide ion has increased, but the silver ion has decreased, because in order for it to reform as the lattice structure, it has to grab those pluses. We can't just pile on a bunch of minuses onto the crystal. Let's look at an example problem here. Let's calculate the solubility of lead chloride, lead 2 chloride, in a solution of 0.15 molar sodium chloride. Now in pure water, well, this would be pretty straightforward. We would take our KSP. It's forming 3 ions, and so it's going to end up as X and 2X. Then you're going to have to square the 2X. When you solve for X, it ends up at 0.016 molar. That would be what the solubility would be in pure water. Now let's see how it looks in a 0.15 molar solution. Start with your ice table. We're starting with some chloride ion, right? So we have to have that as our initial concentration. We don't have any lead ion. It doesn't matter how much solid we have, but it's going to decrease by X. And if that's decreasing by X, then the lead ion is increasing by X, which means that the chloride ion is increasing by 2X. Go ahead and add down. Again, it doesn't matter what we have over here, but we end up with our KSP equaling X times 0.15 plus 2X quantity squared. Don't forget to square the chloride. Now there's 2 ways we could solve for X. The KSP is pretty small, so I'm going to actually show both methods here. If we neglect X, again, only in the addition here, you can't neglect it here because I know it's just going to be 0. It simplifies the math a lot. We end up with 7.1 times 10 to the negative 4th. That would be the solubility of the lead 2 chloride, right? That's how much dissolves, how many moles dissolves in a liter of water. Let's also do the quadratic just to kind of see how it compares. This is what I got from my quadratic equation. When you solve for X, you end up with 7.0 times 10 to the negative 4th, which is essentially the same. It's kind of within a rounding difference. So notice the comparison here. In pure water, it'd be 0.02 almost, 0.016 molar. But in a little bit of sodium chloride, it's 0.0007 essentially. So it really reduces the solubility of the lead 2 chloride. I hope that was helpful, and if you have any questions, be sure to write those down and bring them up in class. All right, this is Mr. Yergler signing out.